The Nuclear Science Applications Project will be a multi-purpose facility dedicated to training the next generation of nuclear experts. It will develop advanced technologies for the diagnosis and treatment of diseases, development of pharmaceuticals, restoration of the environment, management of waste, and non-destructive testing of materials. In each of these areas, nuclear technologies will be transferred from research to practical applications for the benefit of humanity and the care of our environment. Idaho State University and the Idaho National Engineering Laboratory have a long history of cooperation in education, outreach programs, and collaborative research. The INEL is a world-recognized center for nuclear research and its applications. Because of its close proximity to ISU, it serves as a key resource for the NSAP facility. ISU is also a uniquely attractive site for this project because of the programs mandated by the state of Idaho, such as nuclear science and engineering, pharmacy, radiological science, nursing, health physics, and other health-related professions. The College of Pharmacy has become recognized nationally for its application of nuclear medicine. The College of Engineering educates students in nuclear science and engineering. While nationally the number of nuclear engineering programs is on the decline, the state of Idaho, with Department of Energy encouragement, has authorized a new PhD program in nuclear science and engineering at ISU. The Department of Biological Science examines the state's ecological problems and has a national reputation in environmental biology. The College of Pharmacy, the College of Engineering, and the Department of Biological Science share responsibility for the environmental restoration and waste management program. The Department of Physics operates the Health Physics program, providing training for radiation protection. Physics also houses the Particle Beam Laboratory, where particle accelerators are used for research in areas such as hazardous waste identification, pollution measurements, and non-destructive materials testing. All these programs will benefit from the NSAP facility. The proposed facility would be located on the ISU campus and would be accessible to local medical centers. It would house a state-of-the-art trigger reactor. This would replace the existing College of Engineering reactor, which is 25 years old and which is nearing the end of its useful life. In addition to the reactor, the building would house particle accelerators similar to those already operated by the physics department. They will provide particle beams for medical, waste, and material science uses. These accelerators would supplement the reactor's production of isotopes for medical treatment, diagnosis, and pharmaceuticals. One opportunity for the NSAP facility is a familiar one. Boron neutron capture therapy is receiving worldwide attention as a potential radiation treatment for inoperable brain tumors and melanoma. The INEL and ISU are developing strategies for this new neutron therapy. Patients ingest a special drug, a boron compound. The drug circulates in the bloodstream, and when it reaches the brain, the cancerous cells readily absorb the boron compound, while normal cells absorb much less. When that portion of the brain is radiated by a beam of neutrons from the reactor, or perhaps a particle accelerator, the boron atoms each absorb a neutron. The boron nucleus becomes unstable and spontaneously decays into an alpha particle and a lithium nucleus. The energy of the reaction is dissipated within the cancer cell. Since each cancer cell has many such reaction sites, the cancer cell is destroyed. The normal cells surrounding the cancerous mass are not as adversely affected by the neutron bombardment and are able to survive it. The treatment time is only a few minutes long. Such a short time dramatically reduces patient trauma compared to other radiation methods requiring significantly longer treatments. A valuable capability of the reactor is production of radioisotopes to support the domestic pharmaceutical industry, which is presently heavily dependent upon foreign sources. The new facility can also work closely with local medical centers or a proposed radiation and oncology satellite unit. Short-lived isotopes can be employed because the needed isotope can be delivered within minutes of its creation. A non-radioactive chemical is placed near the core of the reactor or in the beam of an accelerator. In time, some of the atoms transmute to radioactive atoms and become unstable. The new radioactive isotope is quickly delivered to a special chemistry lab where it is prepared for patient use. With either long or short-lived isotopes, a certain rate of radioactive disintegration is needed to render the organ detectable by the imaging equipment. The advantage of having a nearby medical facility is that the patient's exposure time to radiation is greatly reduced. The new facility also presents many other options for the future. Researchers are investigating potential applications that will allow us to clean up and protect our environment. For example, scientists in the particle beam laboratory at ISU have researched quick and inexpensive ways to identify hazardous or benign elements in drinking water or other samples. A beam of charged particles or neutrons can be directed at a sample to cause reactions within it. Detectors monitor the reaction byproducts, and these byproducts can then be analyzed. In a few minutes, elements in the sample can be identified at concentrations as low as a few parts per billion. This technology can determine material content in food samples, air and waste samples, or at waste sites. Both hazardous chemicals and fissionable material can be identified and located for safe removal. In a similar fashion, geologists can use the facility for neutron activation analysis. Although research is still in the initial stages, techniques are being evaluated that will change hazardous substances into benign chemicals and safe byproducts. Even fission products may be transmuted to safe substances. For example, strontium-90, with a half-life of 29 years, may be irradiated so that it turns into a stable element like zirconium or yttrium within a year. The reactor can also be used in non-destructive testing of materials using neutron radiography. With this technique, the internal structure of an object can be visualized, a technique similar to current X-ray technology, but neutrons permit imaging of objects which X-rays cannot reveal. The Idaho NSAP will use nuclear science for the benefit of humanity. In addition to applied research in the areas of nuclear medicine and health, nuclear pharmacy, material science, waste management, protection of the environment, and nuclear physics, the new facility will be ideally suited to further technology transfer in these areas. These peaceful uses of nuclear science will be applied by medical practitioners and others to better control human diseases and solve problems in the environment.